Have you ever looked at a drone, a smartwatch, or even a smart thermostat and wondered, what actually makes it, well, smart? It all comes down to the tiny, super powerful computers that are packed inside. Today, we're going to get right into the nuts and bolts of the fundamental hardware that powers pretty much all of our smart devices. So yeah, let's just dive right in. So here's our game plan. First, we'll break down what's actually inside an embedded system. Then, we'll zoom in on the biggest decision you have to make, choosing the brains of the operation. After that, we'll see how these things actually sense and control the world, talk about the unsung heroes that keep it all running, and finally, we'll walk through the very first steps to bring a brand new board to life. So really, what is that secret sauce? The answer is something called an embedded system. And you can think of it as a dedicated little computer designed to do one very specific job. The thing is, they're hidden inside almost every piece of electronics we use every single day. Okay, let's start with the absolute basics. Every embedded system, it doesn't matter if it's huge or tiny, is built from the same fundamental parts. It's kind of like a recipe that has just a few key ingredients you can't skip. Now, what's really cool about this is how it all breaks down. Every single one of these boards, from a simple little STM32 all the way up to a Raspberry Pi, is built from these core parts: a processor to do the thinking, memory to remember things, a clock to keep everyone in sync, a stable power supply, and, of course, peripherals to talk to the outside world. They're all just different recipes using the exact same ingredients, but each one is fine-tuned for a very specific job. All right, let's talk about the brain of the whole operation. This is, and I'm not exaggerating, probably the most important decision you'll make when you're designing an embedded system. And it really comes down to two main choices: a microcontroller, which we call an MCU, or a system on chip, which we call an SoC. So first up, we've got the microcontroller, or MCU. The absolute best way to think about an MCU is like a really powerful, single-purpose pocket calculator. It's designed to do one thing, or maybe a small set of things, and do it incredibly well with barely any power. It's focused, it's efficient, and it's super reliable for real-time control. And then, on the other hand, you've got the system on chip. An SoC is much more like the brain inside your smartphone. It's a total powerhouse designed to juggle a ton of complex tasks all at once. It can run a full-blown operating system like Linux, it can handle graphics, manage networking, all of that on one single chip. So here's the crucial trade-off, right? Do you need that focused, super low power efficiency of an MCU for a dedicated task, like, say, reading a temperature sensor? Or do you need the versatile, high-level computing power of an SoC to run a web server or a fancy user interface? That's the core question. Let's get really specific for a second. Just look at the memory row here. An MCU, like an STM32, might have its memory measured in kilobits. Meanwhile, an SoC, like the one in a Raspberry Pi, has its memory measured in gigabytes. That is literally a 1,000-fold difference. And this just perfectly shows the design goals. MCUs are built for lightweight, real-time jobs, while SoCs are there to handle the really heavy lifting. Okay, so we've got a brain, but how does it actually interact with the physical world? Well, that's where peripherals come in. You can think of them as the senses and the limbs of your embedded system. They're what allow it to see, to hear, and to act. These 5 concepts right here are the fundamental tools for that interaction. You've got GPIOs, which let you do simple things like read a button press or turn on an LED. Timers let you create super precise delays or control motor speeds. Interrupts let the system react instantly to something happening. And ADCs and DACs, well, they're the bridge to the messy analog world of sensors and signals. This map makes the differences crystal clear. See how GPIOs are pretty much available on all platforms? But now look over at ADC and DAC. That's the ability to read and create analog signals. That's built right into MCUs like the STM32 and the ESP32. A Raspberry Pi, on the other hand, which is an SoC system, doesn't have that. You'd have to add an external chip to do it. And that's a perfect example of why you'd pick an MCU for directly interfacing with sensors. All right, let's talk about the unsung heroes of hardware. We tend to focus on the flashy stuff like the processor and the memory, but without a stable power supply, an accurate clock, and a reliable reset circuit, literally nothing would work. These are the foundations of a stable system, and they are so important. So what does this tiny little number even mean? Well, this is the deep sleep current of an ESP32 microcontroller. We are talking microamps. This ridiculously low power consumption is the whole secret behind those battery-powered IoT devices that you can just stick somewhere and have them run for months, sometimes even years, on a single little coin battery. It's amazing. And this table really puts it all into perspective. I mean, a Raspberry Pi 4 might idle at around 600 milliamps. An STM32 can run actively at just 20 to 50 milliamps. And in their low power modes, oh man, the difference is absolutely massive. It just goes to show you that power isn't some minor detail, it's a core design choice that dictates what's even possible for your project. Okay, so we've covered the components, the brains, and the foundations. Now for the really fun part. How do you actually get a new board up and running? This is where all the theory meets reality. This whole process is called board bring-up, and it's basically a methodical checklist to make sure you don't accidentally fry your new hardware. You start with a simple visual check, you verify your power supply before you ever plug it in, you test the voltages after you power it on, and then finally, you check for a heartbeat over the serial console. Trust me, these simple steps can save you a world of pain. And what is the very first thing you do once you know the board is actually alive? You blink an LED. Now, this isn't just some cute tradition, it is the hello world of the hardware world. A successfully blinking light tells you that your power is stable, your clock is running, your GPIO is working, and that your entire programming setup is working correctly. It is a huge milestone. And here, you can see how that one simple goal, just blinking a light, is done on different platforms. On an ESP32, using the Arduino framework, it's a simple digital write command. On a Raspberry Pi, it's a Python script that uses a special library. It's the same outcome, but the code is totally tailored to the specific hardware and platform you're working on. This quote just nails it. It really gets to the heart of the matter. Unlike, say, desktop programming, where you feel like you have endless resources, embedded development is a game of constraints. It's all about deeply understanding the limits of your hardware and then writing clever, efficient software that works beautifully within those limits. So we've gone on a journey from the core components all the way to the concepts that bring them to life. You've now seen all the fundamental building blocks that power the smart devices that are all around us. So the only question left is, what are you going to build first?